Okay, so moving into chapter 2, and we're going to talk about more details about a distribution, and not just describing the distribution, but a specific location within the distribution. Suppose Jenny earns an 86 on her next stats test. Should she be satisfied or disappointed with her performance? Well, you guys know when you get a test grade, or if you make an 86 and you tell your parents about your test grade, it's, well, I made an 86, but everybody else made a 70 something to make your grade sound better. But if you made an 86 and everybody else made 90s, then you didn't do as hot. So she would want to know how she did in relation to the rest of the class. So here's the class scores. Here are all the scores of the 25 students in her stats class. They've thrown it into a stem and leaf. The distribution is roughly symmetric, no apparent outliers. Jenny made an 86, which puts her here. So she did better than all but 3 students in the class. So she did great. One way to describe Jenny's location in the distribution is to calculate her percentile. Now, you guys have gotten some test data back, some standardized test data, and they have told you what percentile you're in. So if they tell you you're in the 97th percentile, that does not mean that you made a 97 on your test. It means that you scored better than 97% of everybody else who took the same test. So one way to describe Jenny's location in the distribution is to calculate her percentile. The pth percentile of a distribution is the value with p% of the observations less than it. Again, so for Jenny, we found that she's in the 84th percentile. So if she scored better, if she has 3 above her, then she scored better than 21. So I'm going to do 21 out of 25 and get 84%. And this 21 are the ones who are below her score. The 21 students scored below her. She is the 22nd person, and then 3 people scored above her. So that puts her in the 84th percentile. Again, she didn't make an 84, she made an 86. But she scored better than 84% of the class in the class test scores distribution. So percentile. Okay. Cumulative, relative frequency graphs. All right, you know what a relative frequency graph is. But now we're going to talk about what a cumulative relative frequency graph is. So let's look at the ages of the first 44 U.S. presidents when they took office. So we have our classes. They are 5 years in width. And then we've made a frequency table of how many presidents fall into each class when they took office for president. Okay, so that's our frequency table. We would be ready to go make a histogram if we wanted to. So now let's expand this table to include columns for relative frequency, cumulative frequency, and cumulative relative frequency. Okay, relative frequency, you know. Relative frequency is just making it relative to everything else. We're going to turn these into percents. Cumulative frequency, well, cumulative means it's like a running total. So we're gonna add as we go. And then cumulative relative frequency is a running total of the percents. Remember, relative just means percents. Okay, so let's look at this table that they've already made for us just to save some time. So again, this was given to us. So the relative frequency, again, that's just percentages. So I've got 2 out of 44 presidents. That's 4.5%. 7 out of 44 presidents. Okay, so all we're doing is getting our relative frequencies for each of our classes. Okay, cumulative frequency. All right, so notice I start with a 2 and then I go to a 9. So can y'all see that all I'm doing is adding as I go? And then I get to 22. So if that's a 9, then 9 and 13 is 22. 22 and 12 is going to be 34. 34 and 7 is 41. And 41 and 3 gives me the 44. So this number, when you're talking cumulative, should always be your total. It should always add up to your total. Cumulative frequency. It is a running total. So let's talk about what this means. What does this 22 mean? Well, it means that there are 22 presidents who are 54 or younger, because that 22 includes the 2, the 7, and the 13. So 22 presidents were 54 or younger, or you could say were 40 to 54 when they took office. 41 presidents were 64 or under when they took office. Okay, so that's cumulative frequency. Now we're going to do cumulative relative frequency. Well, cumulative we just talked about. Relative, you know, means percent. So now I'm going to take all my cumulative numbers and I'm going to put them over 44 and turn them into percents. And obviously when you're done, you should have 100%. Okay, well, we talked about this 22 number being 54 or younger. So now I can make the same statement, but I'm going to use a percent. 50% of the United States presidents were 54 or younger when they took office. So I can put it in a number or I can put it in a percent. But both of these are cumulative information. Frequency is just like a tally mark. It's total. Relative frequency puts it in terms of a percent. So you've got frequency, cumulative frequency. Okay, if I'm going to do a graph, well, my cumulative relative frequency graph should always climb. It should always start at 0%, and when you're done, you should have 100% of your data. So it should end at 100%. You're going to plot a point corresponding to the cumulative relative frequency in each class at the smallest value of the next class. We're going to talk about that. Start growing at the beginning. Slow growing at the beginning because few presidents were inaugurated when they were in their 40s. Graph is steep at age 50. Growth slows at age 60. So I've got a lot of presidents that are here. And then I would say that is really close. That kind of flattens off a little bit. The growth from 40 to 45 is really low, and the growth from 65 to 70 is really slow. Again, I'm not putting a lot of presidents in that bucket. There aren't that many 40 to 45-year-old presidents, and there aren't that many 65 to 70-year-old presidents. Let's see. Could we figure out what percent of the presidents were between 55 and 59-year-olds, 55 and 59 years old at their inaugurations if we just had this graph to look at? So what percent of the presidents were 55 to 59? Erase this stuff. Okay, at 55, I'm going to say that's about 50%. So I can say that 50% of our presidents were 55 or younger. Okay, 59. I'm going to say that's just under 80. I'm going to go 78%. We're not going to split hairs if you put 79 or 77, but should be just under 80. So what the 78 means is that 78% of all of the U.S. presidents were aged 59 or lower. So can we figure out what percent of the presidents were between these two? Absolutely. I just have to subtract them. 28%. Was Barack Obama, who was first inaugurated at age 47, unusually young? And then obviously you want data to back your answer up. So you can't just say yes or no. So at age 47, here's the ages. At age 47, he is in the, I don't know, maybe 11th percentile. He's in the 11th percentile, which means he is only older than 11% of all U.S. presidents at the age they were inaugurated. Now, flip that around and make a more powerful statement. If he's in the 11th percentile, that means 89% of presidents were older than him when they were inaugurated. And that makes much more of an impactful statement. So my justification here would be, yeah, sure, he's only older than 11% of all U.S. presidents inaugurated at their age of inauguration. Or you could flip it and say Barack Obama is younger than 89% of all other U.S. presidents when they were first inaugurated. Estimate and interpret the 65th percentile of the distribution. 65th percentile. Okay. Let's see, that's 70. So 65th would be here. Let's see if I can make a straight line. Okay. I think I went over a little bit. Hold on. Let's try that again. There we go. 55 and 60. So I'm going to say, I don't know, 58. Okay. Estimate. That's why they're not going to split hairs. If you pick 57 and I pick 58, it's okay. Estimate and interpret the 65th percentile of the distribution. Okay, so I'm going to talk and say what I think it is. And then I want you to pause and write it. And then rewind it and listen to it one more time. Okay? But don't try to write while I'm talking. Just soak it in first. Estimate and interpret the 65th percentile of the distribution. Okay? My estimate would be about 58 years old. The interpretation, about 65% of all U.S. presidents were younger than 58 when they took office. About 65% of all U.S. presidents were younger than 58 when they took office. Okay. I also, one other thing I want to talk about with percentiles. What if I ask you about Q1? Well, Q1 is the 25th percentile. So about there, so I don't know, 52? Q2 is going to be the 50th percentile or the median. maybe 55. Q3 is the 75th percentile. There's 70, there's 75. I don't know, 58 maybe? And then Q4 is the 100th percentile. So that's going to be your top piece, which is going to be 70. So if I give you a cumulative relative frequency graph, I can ask you to find the IQR because you have access to Q3 and Q1. So just make sure that you see how all this stuff comes together. Okay? All right. Check your understanding. This is multiple choice. So tell you what, pause this, read, and if you can see it better on your Chromebook, that's awesome. But pause this, answer these questions, and then hit play and see if you get them right. All right, Mark received a score report detailing his performance on a statewide test. On the math section, Mark earned a raw score of a 39, which placed him at the 68th percentile. This means that he did better than about 68% of the students who took the test. Miss Munson is concerned about how her daughter's height and weight compare with those of other girls of the same age. She uses an online calculator to determine that her daughter is at the 87th percentile for weight, 67th percentile for height. Explain to her what this means. It means that her daughter weighs her daughter weighs more than 87% of other girls her age, and is taller than 67% of other girls her age. Following saying the graph displays the cumulative relative frequency of the lengths of phone calls made from the mathematics department's office at Gabalot High School last month. About what percent of calls lasted less than 30 minutes? Call length 30 minutes. Let's see. Maybe 65%. 30 minutes or more would be 35%. So this is less than, and this would be greater than. Estimate, oh looky here, the Q1, Q3, and the IQR. Love it. All right. Q1 is going to be at that's 30, there's 25. So Q1 I think is, I don't know, 13 maybe, somewhere in that ballpark. Q3, which is 75%. Nope, 75% would be here. I don't know, maybe 32. So IQR 19, is that right? Yeah, 19. And let's see, these are minutes, so I'm going to put units of measurement on here. 19 minutes. Okay, awesome. Okay, this is really cool, and this is very important. Z-scores. Measuring position with a Z-score. Looking at the statistics test scores, where does Jenny's score of an 86 fall relative to the mean of this distribution? Okay, so I know that, what's her name? Jenny. Jenny made an 86. There she is. But I want to know where it is relative to the mean. Okay, well, I can look here and see that the mean of the class was an 80. Okay, so now I'm going to use I'm going to talk some stats here. This was a sample, so my mean is going to be X bar. Okay, so side note, it's mu if it's a population, X bar if it's a sample. So my X bar is 80, and my standard deviation is 6.07. Okay, now again, think about what that standard deviation means. That standard deviation, if I was to interpret it, means that typically test scores will vary about 6.07 points from the mean of an 80. Now look, Jenny made an 86. One standard deviation is 6.07. So Jenny is just barely under one standard deviation above the mean. Okay? But I can standardize that. Like I can put a value on that, and that's what a z-score is. Okay, this is the part that's really important. Standardizing, converting observations from their original values, her 86, to standard deviation units. A z-score tells us how many standard deviations from the mean an observation falls and in what direction. Now, we said that Jenny was just over, just under one standard deviation above the mean. Okay, so I'm going to find Jenny's z-score. So z equals, okay, now this is your piece of data. So that's Jenny's 86. So you always start with your raw piece of data minus the mean, which is an 80, over the standard deviation, which is 6.07. Now guys, look at what this formula does. So number one, it finds the difference here. Well, she's 6. Now what if she made a 74? Then I would do 74 minus 80, and guys, I would get a negative 6. So her z-score would be negative, which makes sense because she would be below the mean. So Jenny right now is an 86. So I know she's going to be above. So now I'm going to do 6 divided by 6.07. And I got 0.988. And again, I'm going 3 decimal places, and I'm rounding correctly. Now, a z-score has no units of measurement. It's measuring how many standard deviations above or below the mean that piece of data is. Now remember, we said that her score of an 86 is just under one standard deviation above the mean. And that's exactly what her z-score told us. 0.998. Number one, it's positive, so I know she's above the mean. And number two, it's almost 1. So she is almost 1 full standard deviation above the mean. Okay? Find the standardized scores, the z-score, for each of the following students in the statistics class. Interpret each value in context. So, we've got Katie. Katie made a 93, and Norman got a 72. I want to find their z-score. Okay, one more time, because the more you hear it, the better you're going to get. So listen carefully. The z-score measures how many standard deviations a piece of data is above or below the mean. Your z-score measures how many standard deviations above or below the mean. So if I'm going to find Katie's z-score, then I'm going to take her piece of data and I'm going to subtract the mean. And I'm going to put over the standard deviation. For Norman, I'm going to take his piece of data, I'm going to subtract the mean, and I'm going to put it over the standard deviation. So now I'm going to type this in. 93 minus 80, enter, divided by 6.07. Now look, Katie, her z-score is 2.1416, so I'm going 2.142. So look, Katie is over 2 standard deviations above the mean. So Katie should be like massively excited because remember, most of the data, typically, most of the data is going to fall within 1 standard deviation of the mean. And here's Katie, 2 standard deviations above the mean. So Katie should be celebrating. Now let's look at Sweet Norman. 72 minus 80, I know it's going to be negative because I know he's below the mean. I got a negative 8. Negative 8 divided by the standard deviation, I got negative 1.318 if I round correctly. Now, for Norman, we knew he was below. But guys, look, he's over a standard deviation below the mean. So not only is he below the average, he's well below the average. He is more than 1 standard deviation below the mean. Okay, it says interpret each value in context. So you need sentences here. So pause and write. I would say Katie's 93 is 2.142 standard deviations above the mean score. Norman's score of a 72 is 1.318 standard deviations below the mean for this test. Notice when I talked about Norman, I didn't say his z-score was negative. I refer to it as a distance, but then I use the word below. Norman is 1.318 standard deviations below the mean. Jenny also earned an 82 on a chemistry test. Okay, well that doesn't sound good. She made an 86 on her stats test. She made an 82 on her chem test. At first she was disappointed. Then the teacher told her that the class distribution of scores was fairly symmetric with a mean of 76 and a standard deviation of 4. And I want to know what test did she perform better relative to the class, stats or chem? Okay, so let's find her chem z-score. So put her score first, 82, minus, they said her mean was a 76. Standard deviation was a 4. I'm going to do 82 minus 76, hit enter, divide it by 4, I got a 1.5. So her chem z-score is a 1.5. Her stats z-score, which we found, didn't we find that? Was a 0.988. So on which test did Jenny perform better relative to the class? And I want some sort of justification. So here's what I would say, and then pause it and write it down. Jenny did better on her chemistry test relative to the class than her stats test relative to that class because she scored a higher z-score. For chem, she is 1.5 standard deviations above the mean. For stats, she's only 0.988 standard deviations above the mean. Remember, z-score measures how many standard deviations away from mean. Okay, check your understanding. Mrs. Navard's statistics class has just completed the first 3 steps of the Where Do I Stand activity on page 84. The figure shows a dot plot of the class's height distribution along with the summary stats and a computer output. Okay, so we have height in inches. It looks like we had 25 kids. I've got an X bar of 67, a standard deviation of 4.29. There's my min, there's my max, there's my 5-number summary. Awesome. Lynette, a student in the class, is 65 inches tall. So she is this person right there. Find and interpret her Z-score. Okay, pause. See if you can go answer all 3 of these. Then unpause it and check your work. Okay, so checking your work. Number 1, so Lynette's Z-score is going to be 65 minus the average of 67 over the standard deviation. I know it's going to be negative. I got negative 4.66. It says find and interpret her Z-score. So her Z-score is negative 4.66, negative 0.466, which means Lynette's height is 0.466 standard deviations below the mean height of the class, or the class's average height. But it is that many standard deviations below the mean, the average for the class. Number 2, another student in the class, Brent, is 74. There he is. Inches tall. How tall is Brent compared with the rest of the class? Give appropriate numerical evidence to support your answer. How tall is Brent compared with the rest of the class? I can't just sit here and say, well, he's the top, in the top 3 people, height of the class. That's not statsy. We got to talk about Z-scores. So if I find Brent's Z-score, so 74 minus 67 over 4.29, I get 1.63. So I'm going to say Brent's height is 1.63 standard deviations above the mean height for the class. Number 3, Brent is a member of the school's basketball team. The mean height of the players on the team is 76 inches. Brent's height translates to a Z-score of negative 0.85 in the team's height distribution. What is the standard deviation of the team member's height? Oh, this is such a great problem. Okay, so number 3. So now we have new data. We have basketball player data. And little Brent is 74 inches tall. But the mean height of the basketball players on the team is 76 inches. Okay, now here's the other thing. It tells me what the Z-score is. And it wants me to find the standard deviation. Okay, let's go back to the formula. Z equals your piece of data minus the average over the standard deviation. That's it in stats symbols. Now, let's go like, I don't know, 8th grade algebra on this thing. So my Z-score is negative 0.85. Brent's height is 74. The average of the team is a 76, and I don't know what the standard deviation is. Guys, this is just an algebra equation. I just need to solve it. So the first thing I'm going to do is subtract my 74 minus 76. So I have negative 0.85 equals negative 2 over S sub x. To solve this, I'm going to multiply both sides by S sub x. So now I have negative 0.85 S sub x equals negative 2. And then I'm going to divide by negative 0.85. And I got 2.35. Now, 2.35 is the standard deviation. Standard deviation has units of measurement. That's inches. A Z-score does not have units of measurement, but a standard deviation does. So be okay with using that formula in a non-straightforward kind of way. Make sure you can plug stuff in and find other things. And finding the standard deviation is a very, very common thing to ask you to find. But they would have to give you this and this and this, which is what they just did. Okay, transforming data. What would happen to a distribution of test scores if the teacher decided to add 5 points to everybody's score? Okay, so let's say we take all your test scores and I add 5 to everybody's score. What's that going to do to the shape, the center, the spread, and the outliers? The shape is not going to change. So if my data is uniformly distributed, or if it's right skewed, or if it's left skewed, it doesn't matter. If I add 5 to everybody's score, everything's just going to shift up 5. So the shape stays the same. Adding 5 does not change the shape. Okay? If the average of that test was an 85, and I add 5 points to every single person's test score, then whatever measure of center you're using, it's going to add 5 to that measure of center. However, the spread is not how high it goes, but how far apart it's spread. The spread is going to be the same. I'm adding 5 to the highest grade and I'm adding 5 to the lowest grade. So whatever the spread was, it's going to be exactly the same. The spread will not change. The max and the min will change, but they'll both change by 5. So when I subtract them, I'm still going to get the same spread. I'll still get the same standard deviation. I would still get the same IQR. Outliers would be exactly the same. Everybody's moving at the same rate, the same pace. So if you were an outlier before, you're still going to be an outlier. What would happen to a distribution of test scores if the teacher decided to count every problem worth 2 points instead of 5 points? Okay, so now it sounds like a curve. If I'm going to count every problem 2 points instead of 5 points, so I'm not adding the same to everybody's test. Think about this. If you missed 3 problems, and originally it was 5 points, that cost you 15 points. But now if you miss 3 problems and there are only 2 points, you've now just lost 6 points. Okay, let's take somebody who's lost or who missed 10 problems. Okay, well if I missed 10 problems and they're 5 points a pop, I just lost 50 points. Well, if I miss 10 problems and they're only 2 points apiece, now I've only lost 20 points. Okay, now think about it. Compare the 15 to the 6 versus the 50 to the 20. The kid that only missed 3 only gained 9 points, while the kid who missed 10 gained 30 points. So not everybody's moving at the same rate. The more you miss, the better this is going to help you. If I only missed 1, I'm going from a 95 to a 98. This kid who missed 10 is going from a 50 to an 80. So it really pulls the back end of the distribution up. It does not help the upper end of the test. It helps the lower end of the test. The shape is going to stay the same. If you're right skewed or left skewed or symmetrical, that part is going to stay about the same. It's really not going to change. Your center is going to increase, but you don't know by how much. Now you say you want to come in here and multiply everything by 2, then it would increase by a multiple of 2, by a factor of 2. The spread, this is going to be less spread out. So the spread is going to get smaller. Again, think about it. If you take your distribution, even if you were left skewed, these are going to only move up a little bit. These are going to move up a lot. So it is going to change my spread. It's going to be less spread out because I'm pulling the back end up a lot. Outliers, really don't have enough information to tell, but it could stay the same or it could change. You would need to recheck. Outliers you would need to recheck. Okay, so this last slide really helps to summarize how adding and subtracting and multiplying and dividing affects a distribution. If you add and subtract the same number from each observation, then you will either add or subtract that number to the measure of center and location. So the mean is going to change, the median, the quartiles, the percentiles, all that's going to either add or subtract by whatever you're doing to your data. It does not change the shape of the distribution or the spread. So your range will not change, your IQR does not change, your standard deviation does not change, your right skewed, your left skewed, your symmetrical, none of that changes. It just takes your shape and scoots it to the right or to the left. Now, multiplying or dividing each observation by the same positive number will multiply or divide that measure of center. So the mean, the median, the quartiles, and the percentiles will all get multiplied by that number. It also multiplies or divides the measure of spread, range, IQR, standard deviation, by that number. It does not change the overall shape. So multiplication does more damage than addition and subtraction. They both change measures of center. But adding or subtracting does not change the shape or the spread. It just shifts everything up or down. But multiplying and dividing does change the spread. It does not drastically change the shape.